Hi, my name is Jason, and this is my assignment 3 for Comp 3132 for the applied machine learning. So I'm going to take you through it. So part A is essentially I'm just running the code and just seeing the results from it. So, I guess I could run it again, but yeah, I guess I could run this part again. So it's going to import all the necessary packages and libraries. But for the most part, I'm just, going along with the code. So there's not too much to really explain. It's just going through how the kernels work, as well as the machine, as well as the models later on, and as well as the convolution. So I'm just running it with the kernels here, just, defining a convo or, yeah, convo. And we're going to go to questions 1A and 1B. Same thing as 2A and 2B. So we're just given a kernel here, and we're just implementing it into the kernel that we have. So we're gonna just display the car image. So here's we have one for 45 degrees. Of course, we got the 45 degrees here, the diagonal, and we're going to do the same thing for B, which is the 135 degrees. So it's gonna show the other way. Implement that, and here we have the model car. Question 2 is gonna be the same terminology, the same style, where we're given a kernel and we're going to implement it within our system. So here we are. It was implemented. Here is what we're going to run it with, and we're going to show the image here, as well as the same functionality here. We're given a kernel and we're going to run it, and the image just popped up here. And also 2C as well. Same functionality as the other parts. So for part B is where we have to create the model, implement the convolution layers and whatnot, just to compare the data. So of course we loaded the data set here. Of course we have it done there. Of course we encoded some of the values. And here we created the model, which I'm gonna just take you through. I'm gonna just explain the parts here, so I know later on I was gonna ask for, to explain the parts of the model, of the layers. So of course we have a convolution, we have the max pooling, we have the flatten, we have the dense, and we have the outer layer. So essentially the convolution, it's pretty much its job is to find small parts of the image like edges, layers, or edges like the corners, specific patterns within the image. The max pooling, that's essentially going to shrink the size of the image, but it's still going to keep the important features that we need in order for our model to do its thing. The flatten is going to turn 2D images into 1D, so it can easily just navigate towards the next part of the model. Of course, we use a sequential model, that's just essentially taking you the sequence of layers that we're going to have for the model. And then we have the fourth layer, the dense, where it's essentially learns the patterns and it learns combinations from the images. And the fifth layer is the output, where essentially it's the final layer and it basically wraps up the model, with the neurons and with the function, with the activation function. Of course, we compile the image here with the optimizer, the loss, and the metrics, and we displayed the summary here. So here we're just defining a custom callback. And here we're training the model. And within these epochs, this is the accuracy that we have, gotten from the model. And here is where we are actually plotting the data. So as you can see, based off this, the training accuracy is super high, but the validation accuracy with essentially new data is not as high. It's about 65-ish%. It kind of plateaus around the 65% mark. With the training accuracy, that skyrockets past 90%. So is there signs of overfitting? Of course there is, because the training accuracy shouldn't be higher than the validation, or at least with this great margin. And it happens around, well, essentially around like the 10th, between the 10th and 20 epoch. That's where the difference really defines itself. So I think I'm pretty much answered. Yep, the 5 layers and the purpose of each layer. Now we're adding one or more convolution layers. So I've decided to just add one more here. As I say, I made a little comment here so you know which layer exactly is it. And I've defined the new model. I've trained it, ran the epoch, and I plotted it. And here we are with the additional layer. So as you can see, the training accuracy is still skyrockets, but the validation accuracy, it just shoots up a bit. So that's the difference between this layer and the previous layer, the standard layer that we're given. The accuracy, it's teetering around 70%-ish. It plateaus around there. With the previous layer, it was between 60 and 65% with the validation accuracy. So that's essentially the difference between these two. And when we get to the final part where we added a dropout layer, so we're going to add that here, the dropout. Essentially is just dropping out, just a randomized size, just to balance things out. It helps with overfitting, and we're going to see that in a bit. So we compiled it, ran the epochs, and we plotted it. But now, as you can see, the training accuracy and the validation accuracy are pretty much balanced in a way. Obviously it's not 100% or like 99% accuracy as we expected, but the overfitting definitely decreased because now the training accuracy and the validation accuracy are more closer compared to the larger gaps that we had previously. So this is essentially saying dropout is one of the ways we can resolve overfitting, which essentially takes out some parts of it in order for the model to completely, do its thing and learn essentially the accuracy that it needs to complete. So that is my assignment for this part, and appreciate you for listening.